Hello, good morning and welcome to this seminar from Lancaster University. It's the latest in a series on developments in materials science in conjunction with the European Regional Development Fund project GISMO. GISMO is Greater Innovation for Smarter Materials Optimisation. And I'm James Stancombe, the project manager for GISMO at Lancaster. We're pleased to be joined this morning by Dr. Ben Robinson, Senior Lecturer in Quantum Nanotechnology and Deputy Director of the Materials Science Institute at Lancaster. He's going to speak on the characterization of thin films and interfaces. Just before we hear from Ben, there are a few housekeeping points. The seminar itself is due to last for 1 hour. Please turn off your camera and mute your microphone at this point if you haven't done so already. If you have any comments on what you see and hear, and if you have a question for Ben, please write them in the chat box, and my colleague Jenny Dybell will collect them up and pose them to Ben at the end of his presentation. Well, that's enough on housekeeping. It's time for the main event. Over to you, Ben.
Okay, thank you, James. Hopefully everyone can see me, everyone can hear me okay now. I'm going to be ambitious. I'm going to attempt to share my screen and watch the chat at the same time. So if there are any comments that come in, I'll try and respond in real time if it's appropriate. So let me just get this going. And hopefully everyone can now see my presentation. Jenny or James, if you can't, just stick something in the chat quickly, but otherwise I'm going to assume that everyone can see that now. So thank you very much for attending this at 9 o'clock on a Friday morning. Sorry, if I could just ask if you could turn your cameras off, please. It's quite distracting whilst I'm presenting. So this is a talk today about some aspects of what we do at Lancaster University. And particularly what I want to say is how we think that this can interface with businesses through the GISMO scheme and what we can offer in terms of materials development, particularly around this thin film and interfaces. So I'm going to talk a bit today about really what is an interface. What do we mean when we say an interface? Everything has interfaces. It might be between different materials, if you think of composite structures or laminates or layers, or it could just be the outer interface between a surface of a material in the outside world, whether that be the air or an under liquid application, whatever it may be. But at some point, the material, the device, the thing we're interested in has an interface with something else. And that's really the domain that we're interested in today. We know that the quality of interfaces can disproportionately affect a material or device's performance. If you think of it at a large level between two laminate sheets, if there's dust, if there's dirt in there, it can really affect the adhesion between those two sheets. If you glue something and you have some dirt on the surface, some chemical contamination, the glue might not stick and things can fall apart. You take this to the extreme example, you weld two plates together, two steel plates, ton steel plates. The structural strength of that device, of that weld, is determined by that interface. And disproportionately, it's affected by a very, very small region just either side of that joint. And that can be very, very small indeed. So really getting down, drilling into these interfaces, into these very small structures on joins, on interfaces, on surfaces, can tell us a lot, not only about how our material behaves, but how we can improve it, how we can modify it going forwards. What this talk isn't today is a talk about my personal research. So a lot of what I do is what we would term blue skies. It's reasonably far down the TRL levels. And I'm interested in quantum interference effects for particularly green energy generation. I'm not going to dwell on that particularly much today. Really, I want to pull out the tools that we use as part of this science, this day-to-day research that we do, and to show you how that they can benefit you and really to help you as businesses develop your materials and your devices. Having said that, I will pull examples from my research to try and illustrate how we apply these tools and where they might be useful. And if anybody does have any interest in these sort of quantum structures, in quantum engineering, in thin films, and particularly around thermoelectrics or green energy, please get in touch with me. I'd be very happy to talk about those in a forum other than this. If anybody hasn't been to Lancaster University before, you've not had a chance to see our campus. This is us. We're very lucky. We're just a couple of miles south of Lancaster city centre, just off the M6. So you can't quite see the M6 in this photo. It's hidden by a line of trees, just to the left of the campus there as you're looking at it. And we're a very science intense, engineering intense campus. We've got lots of facilities, lots of cutting edge research facilities. And we've got some really interesting cross-cutting themes and networks in place. And two of those I'm going to talk about today. Two of those in particular are relevant for the capabilities that I'm going to describe. The first one of those is the Quantum Technology Centre. So this is based in the Department of Physics on campus. So it's about here. This is where I spend a lot of my time. And this is set up as a facility for us scientists, as physicists in particular, to translate our research into real technologies. So not just doing science, not just doing research for the sake of it, but really trying to translate it into real things with practical uses. And that can work both ways. So this is a really nice facility, really nice opportunity for industry to engage with us as well. The other cross-cutting theme we've got is an institute. This is the Materials Science Institute. As well as living in physics, this has homes in chemistry and engineering. And the great thing about the Materials Science Institute, the MSI, is it lets us cut across all those different disciplines. And so if we need some expertise from chemistry and engineering and maybe some characterization from physics, for example, the MSI is a really good way of accessing all of those capabilities. And GISMO is intimately linked to both of these capabilities, the MSI and the Quantum Technology Centre. So again, talking to your contacts in GISMO, either James or Alex, for example, they can absolutely tell you how to access all of these things that I'm going to be showing today. Within the MSI, within the Materials Science Institute, we have four major themes. Today, I'm just going to talk about theme one, which is active surfaces and interfaces. We do a number of things in this theme, but today, really what I want to focus on is our capability to do measurements across multiple length scales. I'm going to focus today on the very small, on the nanoscale measurements, because as I hope I've sort of set out already, they can be disproportionately important to the way materials and devices behave. I'm also going to say some things about how we can modify those interfaces with thin organic films. There are lots of ways you can modify surfaces, lots of things you can do to introduce additional functionality. That might be metal deposition, semiconductor deposition, it might be plasma polymerization. We've already had a talk in this series around the plasma polymerization from Professor Rob Short. If you didn't see that, it is available on the GISMO YouTube channel. If you just search GISMO on YouTube, you'll find that very easily. So I'm not proposing today that I'm going to cover all capabilities. I'm going to give you a snapshot of some of them. The QTC, housed in physics, is home to a number of clean rooms. We have a Class 100, Class 1000 clean room, houses electron beam lithography. And we've had a recent investment from the University of an Xray photoelectron spectroscopy setup. Really nice system. I'm going to show a lot more detail about that in a moment. And also the QTC is home to ISOLAB. So ISOLAB is Lancaster's ultra low noise characterization facility. It eliminates mechanical, acoustic, electromagnetic noise. So if you have systems, particularly electronic systems, for example, that require very high precision measurements that really need isolating from the outside world from noise, we have the facilities to do that. So ISOLAB in particular is available through the QTC, as is the clean room facilities. So we have lots of fabrication capabilities. We have Oxford Instruments, we have Moorfield sputtering, we have Joule fabrication, we have all of the standard wet chemistry and etching capabilities you would expect from a clean room. You can access this on a commercial basis or through partnership with things like GISMO. Again, if there are fabrication capabilities that I'm not touching on too much today that you wish to know more about, please get in touch with us, with Alex or with James or myself, and I can point you in the right direction. And we can absolutely give you more information outside of this talk today about how to access those facilities. So what I am going to talk about today is this overview, I think, of some of the relevant capabilities and techniques that we have that are available through GISMO, particularly to characterize things at the nanoscale. So I'll just very briefly say why we're so interested in this nanoscale characterization, and why you as local businesses developing materials, developing devices should also be interested in the nanoscale. So this is my little scale bar here. Hopefully you can see that. And we can see this going up logarithmically in terms of length scales from the meter scale. I can get my pointer on here. From the meter scale represented by my hobbits here, down to sort of the 100 nanometer scale down here, which is the size of a virus, something we all know a lot about at the moment, down to the scale of 1 nanometer, which is typically the size of a molecule, something like that. If you think about how this applies to a standard structure to a material, and we take two materials joining together, and it doesn't matter if they're soft or hard, the argument applies to both. The materials themselves might be ton plates of steel. They might be microfabricated devices. It doesn't matter. They tend to be of the order of millimeters, centimeters, meters. They're right up that end of the length scale. But that interface, where those materials actually join together and interact with each other, they're governed by properties right down at the other end of the length scale, at the nanometer. So it's almost like you don't care once you get into the bulk material. That doesn't affect that interface. It's those first few, literally atoms, first few molecules that can really determine the structure and the performance of that interface. And when we start to look at things at the nanoscale, our mind immediately jumps to the term nanotechnology. And really, that's what we're talking about now. It's how can we nano-engineer, how can we use nanotechnology to improve these interfaces, these surfaces? And I love this schematic. I use this one in almost every talk I give because I think it really shows where we are at the moment. Rather than relying purely on ultra precise, increasing precision in manufacturing to come down in length scales, to understand how these nanostructures work. Actually, we can use our knowledge of chemistry, and we can use bottom-up methodologies, and we can access from the other direction. So rather than coming from the top down, we're going to be talking about the bottom up. And it brings us, directly into this realm of nanotechnology. It's using those tools that we've developed now to apply them to these real world systems. A lot of the motivation for this work's come from, just to let you know the sort of things that we can do, where this has come from, is really quite interesting properties on the single molecule level. And the reason I'm showing this is just to show some of the scientific background that's led to the developments that we're now talking about. So we're taking the extreme limit. We're going to literally a single molecule between electrodes, and we're measuring those properties. And this is really interesting science. It's really interesting science because it tells us a lot about the fundamental properties of how molecules, of how junctions behave at the nanoscale. However, we would be foolish not to acknowledge that single molecule devices are never going to find everyday applications. Okay, so for me, the really interesting stuff comes when we take this fundamental knowledge that we've gathered from single molecules, from these really small structures, the smallest possible structures that we can measure, and we scale them up. And we have many of them, many thousands, many millions of them in parallel. And now these are thin films. And that's going to lead on to how we can modify our interfaces. So today I'm going to focus on three principal aspects of what we do. I'm going to talk about the design of thin films and interfaces. I'll tell you a bit about some of the capabilities we have for fabrication. And I say again, this is a snapshot of just some of the capabilities. I'm not, for example, going to touch on the atomic layer deposition or a lot of the clean room capabilities we have. That will be covered in another webinar at a future date. And I'm going to talk about characterization of how we do these. And I think it's the characterization that's going to have the most immediate applications to most people on this call. So we can design effectively any structure that we want. And as I say, I'm going to focus on organic films for this talk today. We have numerous fabrication capabilities. I'm going to talk about a couple, which is Langmuir logic deposition and chemical self-assembly. But mainly I'm going to focus on characterization of materials, and particularly characterization using something called scanning probe microscopy. And I'm going to do this in reverse order. So I'm going to start at the end and I'm going to talk about characterization first. The problem with a lot of these interfaces, with these nanoscale structures, is they're very challenging to actually access, to understand. It's not something you can just go and look at under an optical microscope. You need facilities a bit like ISOLAB. You need specialist equipment like a scanning probe microscope. And the reason for that is they're far smaller than light. Light is far too big for the sort of things we want to study. So rather than that, we use something called predominantly an atomic force microscope. So don't worry too much about the way the AFM works. But the snapshot of it is that we take an atomically sharp probe, a very sharp probe, and we scan it over the surface of our material. And we measure the mechanical interactions between that probe and the substrate, between our sample and the probe. And depending on how the probe moves, we can detect that motion, we can detect torsion, we can put electrical current across it so we can measure the electrical characteristics, we can put heat across it and measure the thermal characteristics. But we can map with extremely high resolution the structures and properties of our samples. So I've stolen an image now from a colleague of mine, Sam Jarvis, who is also involved in GISMO. So this isn't mine by any stretch, but this just gives you an idea of the sort of resolution that can be achieved from atomic force microscope. I remember when I was doing my GCSE chemistry, asking the question of my teacher, how do we know what molecules look like? And the answer then was, well, we've inferred it. We've done lots of experiments, and this is the best model. We don't doubt this, but we can't see them. We're never going to be able to see them. I remember that answer very clearly. Of course, that's now patently not true because we can now see individual molecules, as you can see in this image on the screen. So these are the capabilities that AFM gives us. Many different things with AFM. So we can measure not just that surface topography, but we can measure lateral forces. So we can measure friction in a junction. We can measure the thermal transport. We can measure the electrical transport. And also I'll say a bit about measuring the thermopower. There's a lot of interest in thermoelectric energy generation from different materials and different structures. And that's a capability we've also been developing. Excuse me. And crucially, what we can do with this is we can run these in a multiparametric way. So we can correlate these mechanical properties with, for example, their electrical properties. And this becomes really important. It becomes essential if we want to develop and debug faults in structured systems, in layered systems, for example. I'll give you one very nice example of this. This was a material that was grown by some collaborators of ours in France, actually. And they were very interested in scaling up a material called graphene. So graphene, you've probably heard of it, won a Nobel Prize in 2010. It was Andrei Gaiman, Kostya Novoselov down at Manchester University had discovered this. And they discovered it by making very, very small amounts of it exfoliated with sellotape. And they measured the fundamental properties of it and they said, wow, this stuff's going to change the world. And everyone agreed it's going to change the world. And there was a big push to make graphene. And the reason it hasn't quite changed the world yet is actually to make large quantities of it is very difficult. And these collaborators of ours in France, they thought they'd cracked it. And they were growing these thin films, single atomic films, as thin as you can get of graphene on a platinum substrate. But when they looked at it under an SEM, they wasn't flat. It hadn't quite worked. And so depending on how they annealed their material, they got these different structures at the bottom here. And so the question that was posed to us basically was, what's going off? We can see the surface, we can see these weird structures, but what are they? You know, chemically, we know it's graphene. Chemically, we know it's just carbon. Chemically, it's right, but it should be flat. And this is where scanning probe microscopy really can come into its own. So we did a series of studies on this, and this is where now we take this multiparametric approach. So we scanned, using our microscopes, the surface of these materials. And across the top line here, you see these three figures, 1, 2, 3. We see the topographical, so the surface profile of what's going off there. And that's a bit weird. It's a bit interesting. Definitely, there's a change in structure as a function of annealing temperature. But how can we tell what that means? For that, we have to study the mechanics of what's going off in that film. So the nanomechanics, the nanoscale mechanical properties. And we did this with one of our scanning probe microscope setups, something called ultrasonic force microscopy. It's a capability we have in the department. And what we find is we get simultaneously a mechanics map. And the way to interpret these images now is along the top, the brighter it is, the higher it is, the taller it is. Along the bottom line, the brighter it is, the stiffer it is. So what you can see here, for example, is we have these high regions by this red circle correspond with things which are very, very soft. And in this image here, we have these big sort of plateaus of material, which are very stiff. But then we have sort of membrane sheets of materials at the side, which are very soft. So what you can interpret from this is there is a change in the underlying structure. We know the surface doesn't change because we have the chemical mapping of that. That's just carbon. It is the underlying structure that's changing. And now we're using these mechanical maps to understand that actually it is the catalytic surface underneath that is falling away, it's degrading. So you can see in my cartoon down at the bottom here, depending on annealing temperature, it's getting little holes, little fractures showing up in it. Otherwise, it's being completely degraded away. And you can see that in the mechanical maps. This is information you wouldn't access normally just by looking at the surface, certainly not from an SEM or a technique like that. So we were able to go back to our collaborator and say, you have bubbles, you have domes falling. So you need to adjust your catalytic substrate, and you need to adjust your annealing temperature. We started to be able to feed back directly into their manufacturing process now to help them solve these problems. And not only that, we can make an estimation of how they needed to change it, because everything that we do with scanning probe microscopy is quantitative. It's not just making pretty pictures of things. It's actually being able to map things and characterize things and be quantitative about them, to the extent we could tell them exactly how stiff their materials were, how stiff their domes were, and where they needed to go off and modify their procedures and processes to really solve those problems and improve it. So that's one nice example of how we can take these tools, these techniques that were developed very much for these blue sky applications, single molecule measurements, and apply them to real world manufacturing systems to feed back to the companies, to the manufacturers, to the industrial partners, how they can modify their approaches, or certainly at least the areas they need to look at modifying their approaches to really improve their efficiencies and their materials. The depth sensitivity of that process is the order of a few nanometers, and that's fine for most surface structures. We have a thin film on a surface that works very well. But what if we want to look deeper than that? What if we have a big piece of material with many layers in it, for example, and we want to slice through that, and we want to see what that structure looks like? So what happens if we look even deeper? So I have some slides now that were prepared for me by my colleague, Alex Robson, who's on this call, who's a GISMO innovation fellow. And this is really a technique that he pioneered. So he's been kind enough to let me show these slides in the context of this talk. So this is a technique that was developed called beam exit argon ion cross-sectional polishing. That's a bit of a mouthful, so BEXP for short. And this is a technique we can combine with SPM. And so if anybody's familiar with focused ion beam milling, FIB, which is used a lot with TEM, transmission electron microscopy, for example, this is a technique that can give you a huge amount of information about very thin subsurface structures. The problem with that is it tends to be very expensive. It's very, very good, but it's very, very expensive, and it's quite slow. What Alex and other colleagues in the department developed was this modification to what is a relatively cheap, relatively quick and benign argon ion beam milling technique. So this is typically used in the way you can see on the screen now for quite sharp cuts through a material. It's very good. It has a low implantation rate. It doesn't contaminate the surface, particularly if the surface is protected on the cut. But the disadvantage for this is that it's not great for accessing buried information for scanning probe microscopy. So the real stroke of genius that my colleagues had was to angle the sample very slightly. And this is a technique, again, that's available through GISMO and other routes through the department. Again, I would encourage you, if this is something of interest, to contact Alex Robson directly for more information about this. So by angling the sample slightly, I've got a nice animation that shows this in a moment. The aim is that we're going to cut at a shallow angle, and we're going to elongate any buried features in our structures. So think laminate structures, composite structures. We're going to slice through that. We're going to elongate those samples, and that's going to make it easier to measure. So how does this work in practice? We take our sample, and we may have a thin layer of interest on the surface. It may be a buried layer. We'll mount that on our sample stage at an angle. It then gets sanded down, so it's approximately flat geometrically to that angle. It's then protected with a mask. This is done under low vacuum. And then the argon ion beams are used to mill across that surface. So you can see now that interface between that surface layer and that substrate has been elongated. We've stretched it out with a simple bit of geometry. And what we do then is we can see when we look at this, is we get this long, flat, smooth, clean cut area. It's been elongated, okay? So we have the cut area, we have the bulk substrate. You can see on this side, we have our nasty, horrible surface that no one really cares about on this side. But we now have this nice, big, clean, flat area that has been cut in the middle. Much deeper than we would normally be able to access with scanning probe microscopy, but now it's absolutely there for the characterization. Taken to an extreme example here, the final slide I've got from Alex, is a multi-layered, massively multi-layered structure of lots of little semiconductor layers that have been grown by various techniques. You can see through the middle here, the black and white image. This is the focused ion beam and TEM image. Very good, very high resolution, very expensive. Against the top is the topographical. This is the BEXP and the topography scanning probe microscopy. And at the bottom, BEXP and the mechanical scanning probe microscopy. So we can absolutely access all of those sort of details, all of those information, and in fact, far more information, because now we can do electrical characterization, we can do mechanical characterization, things you can't do with transmission electron microscopy on these cut samples. So we can use this in combination not only with those modes I've already shown, the topographical imaging, the mechanical imaging, but we can also do it with some other toys that we've developed here. So these are two techniques particularly focused around thermal properties of materials. For anybody who's interested in, for example, thermal barrier coatings or thermoelectric applications. I won't dwell on the technical aspects of these too much, other than to point out that these are available, again, through GISMO. So on the left here, this is a thermoelectric force microscope. So this is, again, using our non-destructive characterization capabilities. And now we're taking our material of interest and we're applying a temperature gradient to it. So we're warming up one side. So one side is hotter than the other. We then land our scanning probe on the surface. And if you've chosen your material correctly, most semiconductors, most organic materials will exhibit something called the Seebeck effect. And this is the generation of an electric voltage, thermoelectric voltage from that temperature gradient. There's a huge push around the world at the moment for thermoelectric materials. It's seen as being one of the potential answers to the carbon crisis we have at the moment, and a key aspect of this aim to be carbon neutral by 2050. Another technique that we have, and again, this I can't take credit for, this was pioneered by a colleague of mine, Oleg Kolosov, who I know a number of people on this call are familiar with. This is the scanning thermal probe microscopy. And this is where you can extract actual thermal conductivities from materials. And it can be done in ambient conditions, real world applications. It can be done under liquids, or it can be done in ultra high vacuum. So again, if you're interested in thermal properties of materials, I really would encourage you to get in touch with us, and I can say much more about those if that's of particular interest. One of the most important properties, I think, of many coatings that we look at, many interfaces, are the electrical transport properties. And again, using a modified version of this scanning of this this electrical probe up here, we can extract electrical properties. We can sweep current voltage properties of our samples, of our interfaces. And crucially, once we can extract those current voltage properties, we can do a bit of manipulation, a bit of maths, and we can extract the exact electrical conductivity of those films. So I hope that I've just given you a quick overview of the capabilities that scanning probe microscopy give us in studying junctions of interfaces of surfaces between different materials, whether they be layered materials, composites, laminates, or bulk materials that have been joined together. We have a wide variety of tools for studying those interfaces. But they are not generally chemical sensitive. Often we're interested in the chemical behavior of our surfaces, of our interfaces. So combining with our scanning probe microscopy, we use a technique called X-ray photoelectron spectroscopy. This is the new system available through the Quantum Technology Center housed in the Department of Physics that I hinted at earlier. So I'm sure a lot of you are familiar with XPS and the capabilities of XPS. We provide an X-ray illumination, X-ray spot, and that can be down to sort of 15 micron spot size in this system. And that X-ray excites the electrons in our surface chemicals, in the chemicals on our sample. They get ejected. We can pick up those electrons that are ejected. And by measuring the energy that those electrons are ejected with, we can very precisely say what the chemical environment was they came from. So precisely that we can distinguish between a carbon-carbon bond, for example, or a carbon-nitrogen bond, or a carbon double bond carbon. Really very incredibly precise chemical mapping capabilities. So this is the sort of information we get out of that. We put in a sample, this one up here. So this was created by a plasma coating. We do our wide spectrum scan. So this is our survey scan. We see very quickly that predominantly this is made of carbon, nitrogen, and oxygen. So on a first point, that makes a lot of sense. We zoom in on these peaks and we do high resolution mapping, and we can pull out very clearly all of these different carbon species, for example, nitrogen species. And it gives us real chemical information about a real surface. This isn't something that's inferred from bulk measurements, for example, from liquid measurements in NMR or mass spectrometry. This is true on-surface device properties. So contamination from manufacturing processes, for example, defects that come from transport. These are the sort of things that will be picked up here. One of my favorite examples actually of the use of XPS was when I was working in Brisbane a few years ago. And one of the local breweries came to us, and they couldn't understand why the beer, it was the Castlemaine brewery, they couldn't understand why the beer was going flat in their new plastic bottles. And through the chemical analysis, through the XPS analysis of the bottles, actually, we found out that there was an excess of oxygen in the polymer of the bottle, and the oxygen was reacting with the carbon dioxide was replacing the carbon dioxide in the beer, and so the beer was going flat. So they had to go off and change their plastics, their bottles. So again, real world examples of how this can be used. So if I go back to my structure for what I wanted to say today, taking this reverse order, we have the capabilities to do fabrication as well. And again, by no means am I going to have time today to talk about all of the capabilities that we have. So I'm going to focus on what I find particularly interesting, which is organic films for modification of surfaces and interfaces. The use of metals, of semiconductors, of layered structures, two-dimensional materials, quantum dots. these are all things that we can do, and we'd be very, very happy to talk about in the future. Please just let us know if you want more information about those. So the first of these techniques I want to mention today, again, is this industrially relevant technique called Langmuir logic deposition. I do a lot of work with a company in Singapore who have make solar cells, and they use Langmuir logic deposition to transfer organic layers to the surface of their solar cells. Actually, it's amazing. They have one of these troughs that I'm about to show, and it's 5 meters wide. So imagine it's as wide as a swimming pool. It works on exactly the same principle that you see here. So we take, for Langmuir logic deposition, we have our surface, we have our material. You've made whatever it is you want, and you want to coat it. You want to put some functional coating on there now, either to protect it against the outside world. So that might be for antimicrobial applications. It might be to make it hydrophobic. It might be to promote adhesion to the next layer that's going on there. One of the ways that we can put a very thin film, a single molecular thick film on there, is using this technique of Langmuir logic deposition. So in this case, I have a trough that's filled with water. I have various properties to measure what's going off here. And I have my substrate, I have my sample. It's already in the water, so it's underwater. And then what happens, let's be ambitious and see if the video works. Yeah, I bring my material of interest down and I spread it onto the surface of that water. So I've now put a layer of my chemical to modify my substrate on the surface of the water. And then I'm going to squash it together, and I'm going to watch how that behaves as I squash it together. And so I want it as a densely packed monolayer. Once I've got that densely packed film on the surface, I pull my substrate. You saw this blue substrate go through the water. I pull that out and I keep squeezing the film, and I push my film of interest onto the surface. And we can do this in many different ways. So here you've seen a single example where it's deposited on both sides. We can easily deposit on a single side. We can deposit multiple layers. We have multi-compartment troughs where we can deposit different materials systematically. It allows us to produce very densely packed, large area films and material. So these were some nanoparticles. So this was done in collaboration with a partner in Spain. And again, this was solving an issue they had about densely packing of particles on the surface. So typically their process used water here, and you can see there's defects and there's problems in the packing going off here. Using our knowledge of how the materials behave in Langmuir logic deposition, we were able to change that water for DMSO and solve a lot of those problems around the packing, around the density on the surface. These were for photonics applications. So these were forming the basis actually of a new generation of light emitting diodes. So again, directly feeding into a manufacturing problem that these partners were having. Another capability I briefly want to talk about is a way we can go about measuring the interactions of these surfaces and films with the outside world. So this is a technique we have and we use extensively called quartz crystal microbalance. So this is an ultra precise mass sensitive technique. So we take a quartz crystal, in this case you can see it here in this device. It has electrodes on either side, and where those electrodes overlap, if we apply an alternating electronic field across those electrodes, the whole crystal vibrates. And if we measure that vibration, we can tell what's going off in terms of the mass on the surface and also the mechanics of that mass. So we can do interesting things like measuring the thickness of materials. We know how much mass is on there, we know how big the electrodes are, we know how thick it is. If you're packing materials on the surface, we can tell about their tilt angle. So we can get lots of very quick, very precise information about how we're modifying our surfaces. And we can tell how they're behaving, how they're interacting with the outside world. So in this case, this was a material, again, a two-dimensional material, graphene-based material, that was designed to interact with, well, the application was underwater. But there was swelling of the material going off. There was water ingress into the structure. Using the QCM, we were able to monitor that and actually quantify the depth penetration of the water through the film. But to the extent that we were able to, again, influence the manufacturing process with how thick the barrier coatings had to be for these subsea applications. And we can do the same with water vapor. So if you're working in an environment which is very moist, not immersed, but very moist, again, we can tell a lot of information about how the moisture, how liquid content is binding to samples and how it's affecting them. Another way we can modify surfaces, we talked about Langmuir logic deposition, that's one example. Another example is a more traditional chemistry-based route, which is something called molecular self-assembly. I don't want to dwell on this too much because molecular self-assembly and chemical functionalization is a huge topic in its own right. Really, what I just want to give you a very quick example of the sort of approach we can take and how it can apply to your business. We can build materials step by step. So we have what I call a chemical toolbox. We have a large variety of materials, and they can be electroactive, they can be thermoactive, they can be hydrophobic. The choice is almost limitless. And what we know is how to build these things up in a bespoke way. So if you look at this chemical structure I put here, don't worry what this chemical structure does. All you need to do is appreciate that it's very complex and it's highly asymmetric. To make this in a lab, to go and buy this as a bespoke chemical would be prohibitively expensive. The yields on it would be tiny, less than 1%, I would imagine, for this, if it was made in a traditional synthetic route. But building it up step by step, almost like a jigsaw, actually makes this very cost effective and very quick. I'll show you an example. If we take electronic properties of quite a complex molecule, this is just to demonstrate the way we can tune functionality of our films. I can grow my first layer on a substrate. This is gold in this case, but that, again, that can be tailored. And I get no interesting electrical properties here at all. It just conducts. I can then modify that surface. Side product, the waste product here is just water. And we can change the way current flows through that structure. It's now acting as a thin diode structure. It's rectifying that current. Or I could decide, actually, I want it to rectify the other way. So again, very simple. Byproduct is only water, very quick, very cost-effective synthesis on a surface. I can measure it again, I can switch it the other way. So we have these capabilities, this toolbox of techniques for growing these materials. And that brings me really to this final point in my backward structure. We can characterize interfaces, we can characterize surfaces at the nanoscale, the topographical, the mechanical, the electrical, the thermal properties. We can do that in a multiparametric way to really understand how your materials, how your devices are behaving. Where required, where appropriate, we can offer routes to modifying those interfaces. So you think about my first example I gave at the very start, dust or dirt on two surfaces you're trying to glue together. We know how to modify those surfaces so there is no dirt, there is no dust there. We know how to modify that glue so that it sticks better. We can help with all of those aspects of how your materials perform, which brings us to the point about design. And I'm not going to say anything in this talk about design because this is where we want to talk to you. This is where we want to understand the problems you have with your materials, with your devices. And we want to understand how we can engage with you and how we can best support you to develop those materials and devices using those tools and those techniques I've outlined over the last 50 minutes. So I'm going to end there. That's 50 minutes. I want to leave a bit of time for if there's any questions. I've just acknowledged this is by no means a complete list of everyone who's been involved in everything I've shown today, but the people working with me at the moment who have really done a lot in the development of the techniques and the processes that I've shown today, based at Lancaster, I acknowledge here, plus the people who have given us the money, including ERDF through GISMO. So I'm going to shut up, and I'd be very, very happy to take any questions on anything I've spoken about, or anything more broadly around the materials and characterization, the capabilities we have at Lancaster. I can't promise I can answer everything, but I'm pretty certain I can point you to the right people who can answer anything. Thank you.
Thank you, Ben. That was a really interesting seminar, very thorough. If anybody does have any questions, please put them in the chat. We do have one that we got earlier from Mark. How do you control the Argon, I think that's polishing technique, to minimize damage to the exposed surface? Okay,
yeah, so I'll tell you what, let me just stop sharing so that we're not staring at that. Yeah, look, okay, thank you, Mark. That's a really interesting question. In most instances, the honest answer is that people don't really care about their surfaces. So the exposed top surface of the sample as it arrives can get contaminated through the process. Crucially, through the argon ion milling, the cut sample, that cleaned sample, cleaned layer that you're trying to access, that remains very clean. Materials constantly being pushed away from that, being polished away from that. So when that comes out of that cross-sectional technique, it's very, very clean. It's pristine. If you want to keep the top surface clean at the same time, that's fine. There's a technique where we can coat a thin polymer layer onto the surface, something like PMMA, to protect that top surface and wash it away afterwards, just using standard solvents. So really, it's a case of understanding where in that structure you're interested in probing. For most cases, you don't have to worry about the top surface, but if you are worried about the top surface, there are ways around protecting that. And again, that's a reasonably standard thing to do, so that's completely accessible through that technique.
Great, thank you, Ben. Another question from Jamshed. Can the AFM deal with biomolecules in water at, for example, 37 degrees Celsius?
Yeah, so this is, again, it's a really interesting technique. The very short answer is yes. The more nuanced answer is it depends what information you want to get out of the biomolecules. Most people would wince at the idea of putting water in a £250,000 microscope. But actually, a number of the studies that we've done at Lancaster over the last few years have done exactly that. So we've got a lot of experience in how to contain small amounts of water in an enclosed system to study in the AFM. Heating it up to 37 degrees, that's absolutely fine. There's no challenge with that. Through the thermoelectric probe microscope and the thermal microscopes that I showed earlier, they have a small heater under the sample. So if the biomolecules are on the heater or in contact with the heater, we can get that up to 37 degrees. We can encase it in water. At that point, topographical and mechanical measurements are relatively straightforward. Obviously, you can't do electrical characterization. If you have a water environment, electricity and water don't mix very well. Well, they mix too well, really. but the characterization of the electrical properties isn't really possible. But all of those other properties that I've shown today, they can be extracted in that environment.
Thank you, Ben. We are running out of time. If anybody has any other questions, you can either put them in the chat and we can forward them on to Ben, or you can email us at gizmo@lancaster.ac.uk. I'm going to hand over to James now, who is going to just talk a little bit about the GISMO project and other ways to contact us.
Thank you, Jenny, and thank you, Ben, too. As Ben mentioned earlier, that whole toolbox of technology and capabilities around characterization at Lancaster is available to you through the GISMO project. And we have a wide variety of ways that we can help you to put your materials to the test. So if you'd like to find out more about the GISMO project and how you can get involved, there are a number of ways of doing that. Check out our website, smarter-materials.co.uk, or hook up with us via Twitter and LinkedIn. And as Ben mentioned earlier on, you can see a little bit more about our capabilities and also watch some of the previous seminars that we've run on our YouTube channel. And today's seminar will be on the YouTube channel a little bit later on too. But yes, if you'd like to get in touch, good and quick way to do that is via email, gizmo@lancaster.ac.uk. Now we've got a couple more seminars coming up from Lancaster University very shortly. The first one is with GISMO's European Regional Development Fund stablemate, the Next Gen Chem project, which works with companies in Lancashire particularly, and that's looking at innovation through sustainable chemistry. So how embracing sustainable chemicals can help you drive innovation in your business. And then in about a month's time, 18th of June, we'll come back to the next in the GISMO series when Dr. Julien Doucet, our GISMO Innovation Fellow, will discuss new synthetic techniques for post-polymerization functionalization. So book early to avoid disappointment on those. But other than that, I'd like to thank you for taking part this morning. Thank you for your attention. And we look forward to helping you through the projects that we have running at Lancaster University and to seeing you at our next set of seminars. So I hope you have a good day and a good weekend coming up, and good morning to you all. Goodbye now.